Welcome to the Deep Dive, where we take the source materials you care about and really try to extract the knowledge you need fast.
Get right to the core of it.
Exactly. Today, our mission is to understand the essential building blocks of AWS cloud architecture. There's so much information out there, it can feel a bit like a maze.
It definitely can. Overwhelming sometimes.
Right. But we've sifted through the material for you, and we're here to highlight the key concepts. Think of this as your shortcut, maybe, to wrapping your head around what makes AWS tick.
Yeah, we want you to walk away with a clearer picture of how AWS is designed, how it achieves that reliability, handles growth, and keeps things secure.
So just to give you a quick roadmap for today's exploration, we'll dive into elasticity and scalability, basically how AWS cleverly adapts to changing demands on your resources.
Very important concepts.
Then we'll look at high availability and fault tolerance. That's all about keeping your systems up and running smoothly, minimizing downtime.
Crucial for any serious application.
We'll also unpack reliability and resiliency, how systems are actually designed to bounce back when things inevitably go wrong.
Because they sometimes do.
Then we'll shed some light on monitoring and visibility using Amazon CloudWatch, and also how AWS CloudTrail provides that vital audit trail.
Seeing what's happening and knowing who did what.
We'll also cover some essential disaster recovery strategies, talk about the big differences between monolithic and microservices architectures.
A really key architectural choice.
And finally, we'll touch upon the AWS shared responsibility model. So the goal here is a clear, actionable understanding of these core ideas, almost like a cheat sheet to how AWS works internally.
Sounds good. Where should we start?
Let's dive right in with elasticity and scalability.
Okay. So thinking about how your needs change, right? Maybe day to day, maybe hour to hour. That's really where elasticity fits in.
Okay, elasticity. So at its heart, it's the system's ability to automatically adjust its resources to match the workload, right? The ups and downs.
Yeah, think of it like adapting, like a system that can stretch or shrink as needed.
I like the thermostat analogy. From the source, it turns the heat up or down automatically. AWS elasticity is kind of like that, but for your computing power.
And the key word there is automatically. The source is really stressed, this automatic provisioning, adding resources, and deprovisioning, taking them away.
And that directly impacts cost, right?
Absolutely. That's a huge benefit. You're not paying for idle resources for capacity you're not actually using at that moment. It's like paying for electricity only when the lights are on. Much more efficient.
Makes sense. And the material breaks down scaling out versus scaling in. Scaling out means adding more instances, more servers to handle more load.
Correct. Increasing capacity horizontally. More workers on the job, so to speak.
And scaling in is the opposite, removing those extra workers when they're not needed.
Exactly. Reducing capacity when demand drops off. Like that restaurant example, opening more tables at peak time, closing some off when it's quiet.
And AWS give you tools for this.
Yes. A core tool mentioned is EC2 auto-scaling groups. These let you manage a collection of your virtual server's EC2 instances and automatically adjust the number based on rules you define.
So if my website suddenly gets a huge traffic spike.
Right. Your auto-scaling group can automatically launch new instances to handle that surge. Then, when the traffic dies down, it can terminate those extra instances you no longer need. All hands off.
That's pretty powerful. Keeps things smooth for users without needing someone to manually intervene.
Okay, so that's elasticity reacting to the immediate ups and downs. How does scalability differ?
Scalability is more about the longer view. It's about the system's capacity to handle growth over time, sustained growth.
So elasticity is the short-term reaction, scalability is the long-term capability.
You got it. If elasticity is handling daily traffic spikes, scalability is ensuring your architecture can cope if your user base doubles over the next year, or if you start processing way more data. It's about planning for that future expansion.
Okay. And are there different ways to scale? Yes. Similar to elasticity, the sources outline two main types: vertical and horizontal scaling. Vertical scaling is scaling up or down.
Like making one server more powerful.
Exactly. You increase the resources of a single instance, more CPU, more memory, like upgrading your laptop to make it faster, beefing up that one server.
Got it. And horizontal?
Horizontal scaling is scaling out or in. This involves adding or removing more instances. So instead of one giant powerful server, you have multiple, maybe smaller servers working together in parallel.
And that's often preferred in the cloud?
Generally, yes. It tends to be more flexible, often more cost-effective, and avoids having a single point of failure. You distribute the load.
Okay, so quick recap. Elasticity, automatic short-term adjustments for cost efficiency. Scalability, ability to handle long-term growth, either vertically, bigger instances, or horizontally, more instances.
Perfect summary.
All right, let's shift gears to keeping these systems actually running reliably. High availability and fault tolerance.
Yeah, the goal here is pretty straightforward. Keep things running smoothly. Keep services accessible to users as much as possible. The sources even show those uptime percentages like 99.9% or 99.99%.
Seeing those numbers really drives home the point, doesn't it? So high availability, or HA, what's the core idea there?
HA aims for, well, very high uptime by minimizing the downtime when something fails. The common strategy is redundancy, having duplicate systems ready to take over.
So if one part breaks, a backup kicks in quickly.
Right. There might be a very short interruption, a brief blip maybe, but the backup system takes over and the service remains largely available to you.
Okay. And how does fault tolerance differ? The source implies it's even more resilient.
It is. Fault tolerance aims for an even higher level, essentially trying to prevent any noticeable impact on the user during a failure. No blip.
How does it achieve that?
Typically by running multiple identical systems simultaneously, all actively processing the workload. If one system fails, the others just carry on seamlessly without missing a beat. The user doesn't even know anything happened.
Ah, like the airplane engine analogy from the source. If one engine fails, the others keep the plane flying. Passengers are unaware.
Exactly, that kind of seamlessness. It's designed for zero interruption.
Now, there's a service mentioned that helps with both HA and scalability. Elastic load balancing, ELB.
Yes, ELB is critical. Think of it as a smart traffic controller for your application. It sits in front of your pool of servers, your EC2 instances.
And what does it do?
Two main things relevant here. First, it distributes incoming user traffic across multiple instances, so no single server gets overloaded. That directly helps with scalability.
Spreads the load. Makes sense.
Second, for high availability, ELB constantly checks the health of the instances behind it. If it detects an instance is unhealthy or has failed,
It stops sending traffic there.
precisely, it automatically reroutes the traffic away from the faulty instance to the remaining healthy ones. This maintains the availability of your application even if individual servers fail, like air traffic control diverting planes from a closed runway.
Okay, so ELB is like this front door that manages traffic flow for scalability and reroutes it for availability. Got it.
It's a key piece of the puzzle. Now, building on this, let's talk about reliability and resiliency, more irilities.
Right, so the source says a reliable workload is designed to automatically recover from failures and scale horizontally. So it's not just about preventing failure, but handling it well.
Exactly. Reliability is the outcome you want a dependable system. And the source points out that reliability depends heavily on resiliency,
Resiliency.
like the underlying capability.
Yeah, think of resiliency as the application's immune system. It's what enables the reliability.
Okay, so what does resiliency actually mean in this context?
The materials define it as the ability to recover from infrastructure or service disruptions. This includes a couple of things. First, the ability to dynamically get computing resources to meet demand.
Linking back to elasticity again.
Exactly. If there's a sudden need, a resilient system can scale up. Second, it includes mitigating disruptions, things like accidental misconfigurations or temporary network problems. So it anticipates these issues.
A well-designed, resilient system does. It expects failures to happen at some point and has mechanisms built in to handle them gracefully without causing a major outage or really impacting your experience as the user.
So it's proactive, not just reactive, expecting bumps in the road.
Precisely. It's about building systems that assume failure will occur and are prepared to deal with it. Okay, so how do we actually see if our systems are healthy, elastic, resilient? That brings us to monitoring.
Right. Amazon CloudWatch. The source calls it the central hub for real-time monitoring. Sounds important.
It really is. Think of it as the dashboard and the data collector for your entire AWS environment. It gathers metrics data points from almost all AWS services.
What kind of metrics?
Things like CPU usage on your servers, network traffic in and out, how busy your databases are, storage performance, a whole range of operational data.
And what does it do with all that data?
It collects it, aggregates it, and provides statistics. This lets you see trends, establish what's normal performance, a baseline, and generally understand how your systems are behaving over time.
But it's not just looking at graphs, right? There's an active component. Alarms.
Yes, alarms are a very powerful feature. You can set rules based on these metrics. For example, alert me if CPU utilization on my web servers goes above 80% for more than 5 minutes.
And when an alarm goes off.
It can trigger actions automatically. It could tell your EC2 auto-scaling group to add more servers. It could send a notification, an email or text message to your team, or even trigger some automated remediation script.
So it helps automate the response to problems.
Exactly. Proactive management. And CloudWatch isn't just about metrics. It also handles logs.
Application logs, system logs.
Both and more. Through CloudWatch logs, you can collect, store, and analyze log files from your applications, operating systems, and many AWS services. This gives you really detailed insights for troubleshooting or understanding specific behaviors.
Does it track only standard things, or can you customize it?
It supports both standard metrics provided by AWS services and custom metrics that you can define and send from your own applications, so you can monitor things very specific to your workload.
So CloudWatch gives you the big picture with metrics and alarms and the fine details with logs, both real-time and historical views.
Yep, it's your eyes and ears inside AWS, essential for operations and performance tuning.
Okay, now let's switch to accountability, tracking who does what. AWS CloudTrail.
Right. CloudTrail is all about answering the who did what, when, and from where questions in your AWS account. The source emphasizes its role in governance, compliance, operational monitoring, security analysis, risk auditing, basically keeping a record.
Like a security camera pointed at your AWS accounts management activities.
That's a good analogy. It records actions taken by your users, by roles assumed by applications, and even by AWS services themselves as events.
And you can look back at these events.
By default, CloudTrail keeps a 90-day history of these management events that you can view, search, and download directly in the console.
What kind of actions does it actually record? The source mentions API calls to AWS.
Yes, that's a key distinction. It primarily logs calls made to the AWS control plane, the management interface. Things like creating an S3 bucket, modifying a security group rule, launching an EC2 instance, changing network settings.
So not necessarily things happening inside my running application.
Generally, no. Not the internal API calls within your own code, but the calls made to manage the underlying AWS resources themselves.
Okay. And the benefits are pretty clear. Better security, tracking changes, helping with compliance.
Absolutely. It lets you see who changed what, which is crucial for security investigations and troubleshooting operational problems. And having that documented audit trail is often essential for meeting compliance requirements.
What if you need to keep logs longer than 90 days?
For that, you need to create what's called a CloudTrail trail. A trail configures CloudTrail to continuously deliver the log files to an Amazon S3 bucket that's AWS's cloud storage service that you specify.
So you can archive them indefinitely in S3.
Pretty much. You control the retention in the S3 bucket, and you can set up a trail for a single region or, as AWS usually recommends, for all regions to get a complete picture.
And these trails can integrate with other services.
Yes. You can link a trail to Amazon SNS, the notification service, to get alerts when new log files are delivered. And you can send the logs from S3 to CloudWatch logs for more advanced searching and analysis, correlating them with other logs.
Is the data in S3 secure?
Yes. The source notes that log files delivered by CloudTrail to S3 are encrypted by default using server-side encryption, SSCS3, protecting the data at rest.
Okay, the source also mentioned different types of CloudTrail events.
Yeah.
Management, data, and insights.
Right. Management events are those control plane operations we discussed, creating resources, modifying configurations. These are logged by default in that 90-day history, and enabling a trail for them is generally free for the first copy.
And data events.
Data events provide visibility into operations performed on or within your resources. The classic examples are accessing an object in an S3 bucket or invoking an AWS Lambda function. These can generate a lot of logs.
So they're off by default.
Yes, data events are disabled by default, and enabling them comes with additional charges because of the potential volume. You enable them selectively for specific resources you need to monitor closely.
Makes sense. And insights events. Sounds like threat detection.
Kind of. Insights events use analysis to identify unusual patterns of write API activity in your account. CloudTrail learns your normal patterns and flags significant deviations, which could indicate accidental misconfiguration or malicious activity.
Also off by default and charged separately.
Correct. Like data events, you enable insights events if you need that specific capability. Finally, there's log file integrity validation.
Ensuring the logs haven't been messed with.
Exactly. CloudTrail creates a cryptographic hash, like a digital fingerprint, for each log file it delivers. You can use this hash later to verify that the log file hasn't been altered or deleted since CloudTrail delivered it. Really important for audit and compliance.
Okay, so CloudTrail is the verifiable record keeper for your AWS account management. Very clear. Let's change tack now and talk about application structure. Monolithic versus microservices.
Yeah, these represent two fundamentally different philosophies for building applications. A monolithic architecture, as the source describes it, is where the entire application is built as a single, tightly coupled unit.
Everything together. User interface, business logic, data access layer, all in one deployable package.
Pretty much, often called the big ball of mud analogy. All components are interdependent.
What are the implications of that?
Well, for one, if you need to update just one small part, you often have to rebuild and redeploy the entire application. This can slow down development and increase the risk of introducing errors.
And scaling must be harder too.
Right. If just one component, say, the product recommendation engine, needs more resources, you have to scale the whole monolith, even the parts that aren't busy. It's inefficient. And if one component fails,
It can bring the whole thing down. Single point of failure.
that's a significant risk with monoliths, yes.
Okay, so what's the alternative? Microservices.
Microservices take the opposite approach. You break the application down into a collection of small, independent services. Each service focuses on a specific business capability.
Like user authentication is one service, inventory management is another, payment processing is a third.
Exactly. Each one is developed, deployed, scaled, and managed independently. They communicate with each other over the network, typically using lightweight APIs.
The big advantage there seems to be agility.
Huge advantage. Small, focused teams can work on individual services and deploy updates frequently without impacting other parts of the system. If the inventory service needs an update, you deploy just that service.
And scaling is more granular too.
Much more. If your payment service gets slammed during a sale, you can scale just that service up, adding more instances of it without touching the user login service or anything else. It leads to better resource utilization and often lower costs.
So faster development, independent scaling, better fault isolation.
Those are the key benefits highlighted. Of course, microservices introduce their own complexities, like managing communication between services and distributed systems, but for large, complex applications, the agility often outweighs the challenges.
Okay, that makes sense. Let's move to our final technical topic. Preparing for the worst with disaster recovery.
Absolutely critical. A disaster, as defined in the source, is really any event that significantly disrupts business operations or causes major financial harm.
Could be anything from a hurricane or fire to a major hardware failure, a cyber attack, or even just a prolonged power outage.
Exactly. It's a broad definition. And disaster recovery, or DR, is all about having a plan to recover your IT systems and business functions after such an event occurs.
The source stresses that the plan needs to be tested regularly.
Vitally important. An untested DR plan is just a document. You need to know it actually works. And the right strategy depends on your business needs based on an impact analysis or risk assessment.
Which involves defining two key metrics, RTO and RPO.
Correct. RTO is recovery time objective. What's the maximum acceptable downtime? How long can the business afford to be offline? RPO is recovery point objective. What's the maximum acceptable data loss? How much data, measured in time like minutes or hours, can you afford to lose?
And these objectives drive the choice of DR strategy.
Heavily. The source describes a few, starting with the most basic: backup and restore.
This sounds like just making copies.
Essentially, yes. Regularly backing up your data and system configurations, maybe those AMIs, and storing those backups securely, often in a different AWS region. If a disaster hits your primary region,
You restore everything from the backups in the other region.
right. The key here is that you don't have an active DR environment running beforehand. It's cold storage. This makes it the cheapest option, typically, but also results in the longest recovery time, the highest RTO.
Okay, what's the next step up? Pilot light.
The pilot-light strategy involves keeping a minimal version of your core infrastructure running in the DR region. Maybe the core databases are running and receiving replicated data. Maybe key network components are set up.
So like a small flame burning, ready to be turned up.
Exactly. The critical data is already there and replicating. If a disaster occurs, you turn up the flame by launching and scaling out the application servers and other components around that core pilot-light infrastructure.
Faster recovery than backup and restore.
Definitely faster recovery, so a lower RTO. But it also means higher ongoing costs because you have some infrastructure constantly running in that DR region, even when there's no disaster.
So it's a trade-off between cost and recovery speed, driven by those RTO and RPO targets.
Precisely. There are other, even faster strategies like warm standby or multi-site active-active, but backup restore and pilot light are common starting points discussed.
Wow, we've certainly covered a lot of ground today, really dug into those core AWS concepts.
We touched on elasticity and scalability for handling demand, high availability and fault tolerance for uptime, reliability, and resiliency for bouncing back from issues.
Then monitoring with CloudWatch, auditing with CloudTrail, the architectural choice between monoliths and microservices.
And finally, planning for disasters with different DR strategies like backup restore and pilot light.
It really highlights how these different pieces interconnect, doesn't it? They all work together to build that robust, scalable, secure environment AWS aims for.
Absolutely. Understanding how these concepts relate is key. Thinking about elasticity enables resiliency, which supports reliability. Monitoring helps you manage availability and scaling. It's all linked.
So as you, the listener, work with AWS or maybe think about migrating to the cloud, keeping these building blocks in mind is really crucial.
Definitely. Having this foundational understanding helps you make better design choices and operate your cloud solutions more effectively.
Thank you for joining us today.